Okay, for 17b, we have figured out the equation for the standard error. So if we have a box, we know how to find the sum of the box. You just add up all the tickets. We know how to find the average of the box, which is just the sum of the box divided by the number of tickets in the box. Okay. And we also figured out how to find what is called the standard error. What is the standard error? Not how do you find it, but what does the standard error tell us? It's pretty much, well, not pretty much, it is the standard deviation of the results for a particular number of draws. If we're going to do 100 draws from a box, 68% of the people who make 100 draws will be within one standard error of the predicted average, the expected value. Does everybody understand that? So if I make 100 draws, then the results for everybody who does that will be normal, and 68% of the people will be between -1 SE and +1 SE. Okay, and that standard error changes for every number of draws. The standard error for 50 draws is going to be smaller than the standard error for 100 draws. Okay, so how do we calculate the standard error? What was the formula? The square root of the number of draws times the SD of the box. So I have the box right here. I find the SD, whatever it is, and then I multiply it by the square root of the number of draws. And that will tell me the standard error, which is an incredibly simple equation. And the fact that it works that way is pretty insane. In fact, this formula was thought to be true for a couple hundred years, I think, and they had no way to prove it. How do you prove that this works? Well, you pretty much have to do a lot of draws in a lot of different ways and see if it works out. Now, we read about the guy who flipped the coin in the concentration camp like 20,000 times and recorded all the results. That sort of stuff is really, really slow. But in the 50s and 60s, when computers were coming around, we started to use computers to run simulations, and we verified that this formula is actually accurate by just creating a program that pretended to flip a coin or draw, play roulette or whatever. And turns out it does work. Okay, number 1. 100 draws are going to be made at random with replacement from the box 1, 2, 3, 4, 5, 6, and 7. Okay, we're going to make 100 draws. Find the expected value and standard error for the sum. So what is the sum of the box? 15 plus 13 is 33. Did I do that right? 15 and... nope. Sorry. So 15 and 6 is 28. Wow, I was way off. Okay. So that means if you play this game 7 times, you're expected to win $28. The average of the box is simply 28 divided by 7, which is 4. What does that number mean? Each draw is worth $4 on average. Okay. Are any of the draws actually worth $4? In this case, yes. Okay. So my expected value is simply the average of the box times the number of draws. So I'm going to take 4 and times it by 100, and my expected value is 400. That's how much money you're expected to win if you play this game 100 times. Okay? Now, how many people will actually hit 400? Very few. Okay? Most of you will be close to 400, but very few of you will actually hit 400. So we need to calculate the standard error to figure out where people are going to land. So I know that my normal curve has 400 as the expected value, but I want to know how many people, or sorry, how wide is this set here that includes 68%? Well, I need the standard error. To find the standard error, I need the square root of the draws times the SD of the box. So I go into my stat, and I'm going to enter the numbers 1 through 7. Okay, and then go back into stat and do one variable statistic. And that's going to give me the sum is 28, the average is 4, and the SD is 2, or the SD is 2. So the SD of the box is 2, and I'm going to multiply that by the square root of 100, which is 10 times 2, which is 20. What does 20 tell me? That is the standard error, which means you are expected to get 400 plus or minus 20. Another way to say it would be 68% of the people will earn between 380 and 420. Does that make sense to everyone? Okay. So the sum of the draws will be around 400, give or take 20 or so. Suppose you had to guess what the sum was going to be. What would you guess? If you had to guess what the sum was, what's the best guess? 400, because here is the column that includes 400. It's taller than all the others. The 399 column is slightly smaller. The 398 column is slightly smaller. The tallest column is 400. That's the best guess. How far off do you expect to be? 20 or so. That's the interpretation of the standard error. Okay, number 4. 50 draws are made at random with replacement from the box 1, 2, 3, 4, 5. So I'm going to make 50 draws. And I'm going to go ahead and put that in my stats because apparently I don't know how to add things up. I bombed it last time. So I'm just going to get rid of 6 and 7 from this list. And then do a one variable stat. And it will tell me everything I need, which is the sum of the box is 15. The average of the box is 3. And the SD of the box is 1.41, which I believe is the square root of 2. Okay. So the question says, the sum of the draws turns out to be 157. Well, what is the expected value if I do 50 draws? Multiply this by 50. I'm expected to get 150. Give or take how much? Well, I'm going to take the square root of 50 times 1.41, which is the square root of 2. So the square root of 50 times the square root of 2. Oh, don't do it that way. Don't put one square root inside the other. So the square root of 50, and then you have to push right. Oh my goodness, I really messed that up. Sorry. Square root of 50, push right, times the square root of 2, and I get 10. Okay. So number 4 says the expected value for the sum is 150. The observed value is 157. The chance error is how far off was my observation from what I expected? 7. The standard error is 10. Now, would we expect 157 to be pretty likely? Does that seem reasonable? Yes. Which basically is asking, are the numbers in the box equally likely? Yes. We're within one standard deviation. That's totally possible. What if I got 160? Is that likely? That's still pretty likely. What about 165? Now I'm 1.5 SEs away. It can still happen. What about 170? No, that's pretty unlikely. What about 180? That would be pretty impossible. 180 is 3 standard deviations away, which means 3 out of 1,000 people will get that. It can still happen, but it's very unlikely. And in our calculator, once you get 5 standard errors away, the calculator quits even worrying about that. You're so close to 100% that does not happen. Okay. Number 6. 100 draws are going to be made at random with replacement from the box 0, 2, 3, 4, 6. So let's do everything we need, and then we can do the true or false for this. So 2, 3, 4, and 6. One variable stats. And I end up with the sum of the draws, 15. The average of, the sum of the box. The average of the box is 3, and the SD of the box is 2, and my draws are 100. So my expected value is going to be 3 times 100, which is 300. So most of you will be close to 300. The standard error is going to be the square root of 100 times 2, which is 20. So I now know that my 68 window is between 280 and 320. Everybody okay with that? All right, letter A. The expected value for the sum of the draws is 300. True or false? True. The expected value for the sum of the draws is 300, give or take 20 or so. True. False? Oh, oops, good job. So, does the expected value change? No, the observed value changes, so that's true. That's false. The expected value is 300, end of story. The observed value is expected to be 300, give or take 20 or so. Okay, see, the sum of the draws will be 300. False. The sum of the draws will be around 300, give or take 20 or so. That's true. All right.